with an initial condition given. As an example to explain the ideas. So for this one, of course, if you also give a boundary condition, so let's say if it is, if you have the situation that f prime of u is always positive, if you have this restriction, then so this is x, this is y, t, sorry. I can treat t as y, right? So it does not matter. So if you give the initial condition here, if on top of the initial condition you are also given boundary condition here, because of these constraints, it is suitable to give boundary conditions along this side, but not suitable to give boundary conditions here. So if you have this scenario, then the good old DG method can work, right? You can write down the good old DG method. There's no linearity, but that's not an issue. It's not, non-linearity is not the obstacle in this case, because you know that the wind direction does not depend on you, on your solution. The wind direction is always positive. It's always going this way. So you can repeat what we said in the previous hour. You can get the DG method working with it. However, if you don't have this condition, then the boundary condition is usually given both here and here, and the initial condition. Then it's very hard to get the previous DG method working. Then what do we do? Well, we can say that one easy way to get out is to say, I just use the DG method in space to treat f u sub x. I leave t alone for the time being. So this is hybriding, right? So I'm not attempting to use DG on both space and time. There are people who use DG on both space and time. This is called space-time DG, which is also a very active research area, but I'm not going to talk about that. So in my case, I will treat, from now on, I will treat t differently from x. Or if this is 2d, x, and y, so they are treated by DG, but t is treated in a different way. T will eventually be discretized by the usual ODE solver, like multi-step, like lecture2. So this is the lecture2. So then we repeat what we did before, but this time we only do it in the spatial variable x. So basically we multiply it by function v is still 0. We then integrate now, because I treat only the space, I will not have the time, I will not put those boxes, I will just use one dimension. So my notation is simpler. Instead of I sub ij, I only have I sub j, so it's one dimension. So this is j minus half, this is j plus half, the middle could be xj, and the length could be delta xj. So if I have this conservation, I multiply it by a test function, any test function is still 0, I integrate over ij, this is still 0. I repeat the integration by part, thing I did before, only now I don't do it on t. Remember, now I'm trying to treat t differently as x. So t, I leave it alone. I don't do anything to this term. So I do integration by parts only on this x term. So I get this thing, fu times v sub x dx. Then I pick up two boundary terms. Only two, right? Before I have four. So now things become easier. So it's u of j plus half, v of j plus half, minus f of u of j minus half, let me erase it here, v of j minus half minus equals to 0. So this equality holds for every continuous solution of the original conservation law multiplied by any C1 function v. Right? Okay. So the scheme again comes from this equality. So since you have seen the original DG scheme before, what I explained here will be automatic, will be trivial, right? Because I'm just repeating the previous scheme. The only difference is that I'm now doing it only on x, not on t. So what I will do is that I would convert this to a scheme for which I just put a U sub H. Put an H here, put an H here. And what is H? So I want to find UH belonging to capital VH such that for any test function V also in VH, we have this equality, right? So let me erase this line, because this line was when I was trying to motivate the equality, but now I become completely the scheme. So I want to find UH in this function space VH such that this holds. The VH is the same thing as before. So VH is the collection of the functions G, which when restricted to IJ is a polynomial of degree 8. So only now it is one space dimension other than 2. It's the same as before. So you see, the thing is that I have replaced the inequality every U by UH. So I get this equality, but of course, this equality is still ambiguous, right? When U was the exact solution of PDE, it was not ambiguous because I assume U is smooth, at least continuous. But now, since UH comes from this space, which is continuous, then these terms must be given meanings. Again, I use the same philosophy as before. I know that at the k equals 0 level, I should recover my good old first order monotone scheme. I know that for first order monotone schemes, this will be good. So for k equals 0, I should recover monotone scheme. This is my sort of a minimum requirement. So I want to generalize the method to some high order degree, high order polynomial, but at least my method should work in the simplest case, which would be k equals 0. So if you insist that for k equals 0, you recover the monotone scheme, then that already tells you how you should treat these terms. There's no more freedom. So it turns out that this thing should be replaced. First of all, these two things, you don't have to touch them because they are integrals. And this is a polynomial. This f of UH may not be a polynomial, but it's a function of polynomial, which in many cases can be integrated exactly. Even if they may not be able to be integrated exactly, you could use a quadrature of sufficient accuracy. So this is not causing you trouble. These are the guys. So this should be replaced by a monotone flux, which you have seen in this conference a bit. So monotone flux, which depends on two variables rather than f depends only on one variable. Here you have two variables. So you have the minus at j plus half, and you also have the plus at j plus half. In other words, your function at j plus half has a left limit, a right limit. So this is the left limit, this is the right limit, and this f hat is a function of both of them. So this term is replaced by that. By the same token, of course, this is replaced by the same guy, except this will be j minus half, UH minus j minus half, UH plus j minus half. So that takes care of these two guys. These two guys, just like in the previous case, they come completely from within the cell. So that means on the right boundary, you take the left limit. On the left boundary, you take the right limit. That's it. So the method is now defined. So you want to find UH in VH such that this equality by this guy is replaced by this holds for every function V in VH. Okay, so I did not explain what f hat is, but for those of us who have already studied conservation laws, know monotone schemes, would know that this f hat can be a function from a class, which is the first thing is that f hat has to be somehow related to f. In other words, if your function happens to be continuous there, the left limit equals to the right limit, then you better recover the physical flux f. So f hat u is f of u. The other thing is, this is important, is this monotonicity condition. So f hat is an increasing function of the first argument, decreasing function. This is how it got the name of monotone branch. So it's monotonically increasing in the first argument, monotonically decreasing in the second argument. And then finally, f hat is, it has some minimal regularity. Lipschitz would be enough. So it's Lipschitz continuous with respect to both the first and the second arguments. So many things satisfy such requirements. For example, you have the Gordonov flux, Lars bridges, Chris-Osher, many things. In system cases also you have Gordonov flux, you have HLLC, you have Lars bridges, you have many things. Osher, many flags that you can use. So here, the DG method did not invent anything new. It borrows this flux definition from finite volume schemes. So that is why DG method is very close to finite volume. This is that it uses directly the flux. This also means that there is not a single DG method. So you cannot say, oh, I have this nonlinear conservation law, I'm using DG. So this is not enough description to let people know which DG you are using, because you could be using a different flux than the other guy. So of course then you compute and get different results, which is perfectly okay, because there is not a single DG method. There are class of DG methods. If you change your flux, then your DG method will change. So there are some freedoms here that you can choose this flux. Okay, so let me first explain how this method is implemented, because that is important to understand why it becomes popular. Basis. To implement the method, again, you choose a basis of VH. You choose basis of VH, which you can again denote it by phi j of L of X. This is for in Ij, so this L goes from this time this is a one-dimensional thing, so I can just use 0 up to small k. I don't need capital K because I need, right? So I know that for polynomial of degree k, I have k plus 1 numbers. Degree 1, I have 1x plus degree 2, 1x squared is 3x. So it's always a small k plus 1. So if I start from 0, just have that. So this is the basis in Ij. And j runs from 0 to capital N. So this is the basis. Then UH would be just summation of this basis L from 0 to small k of UJL phi JL sub x for x belonging to Ij. Then this guy becomes Ij summation L from 0 to small k, UJL phi JL of x. So this is the UH sub t part. So let me see, where should I put the sub t? So the t dependency is now through those coefficients, because I did not discretize t yet. So of course for each t I have different coefficients. So these coefficients are functions of t. Hence, this you can take the derivative with respect to t. Yeah. Yeah. Partial derivative with respect to t times v. V I can take it again to be phi of, I think I used m for jx dx. So that's the first term. The second term is f of this guy times the derivative of this guy dx. So that's the second term. The third term, let me just denote it by j plus half times phi mj xj plus half minus f hat j minus half times phi mj Sj minus half equals to 0. And what is this thing? This thing is because it takes a bit of space to write. Let me put it up. Put it up so I can write it down here. This thing is here, right? It's defined here. So it is f hat, which is the monotone flux, evaluated at u minus, which is u minus at j plus half is in cell ij. So I use the definition in cell ij, which is u of jl, phi of jl of xj plus half. This is one thing. The other thing is UH plus j plus half, which is actually the polynomial in my right neighbor, right, evaluated at j plus half. So here I would use, and here is when you talk to your neighbor, I would use UL j plus 1, phi j plus 1L as j plus half. So here you talk to your right neighbor through this flux. You take the polynomial in your right neighbor, you evaluate that polynomial at the interface to put it in the flux definition. So this is this f hat. This is this f hat. Of course, this f hat is the same, you just shift the index by 1. So this is how you implement it on a computer. So if you look at this, so let me still put it here. If you look at this scheme, if I know the function, I know the numerical solution at time level n, which means I know all these coefficients. Right? At the time level n. Then I would want, let's say if this time derivative is discretized by Euler forward, I would want to determine the same set of coefficients time level n plus 1. What do I need to do? Well, all these terms will be at time level n, for which I can just compute, because I already have my numerical solution at time level n. So the only place that I need to worry about is this first term, because it has a time derivative. But the first term is a very simple thing, because first of all, I take the summation out, right? And I take also the coefficient out. Because the coefficient is a function of t, has no x in it. So if you integrate over x, you can just move it out, it's constant. So what I'm left with is this thing. Is phi jl of x, phi jm of x dx. Now this guy, this is a matrix, right? Because L runs from 0 to small k, M runs from 0 to small k, so this is k plus 1 times k plus 5 matrix. In P1 is a 2 by 2 matrix. In P2, this is 1D. In P2 is a 3 by 3 matrix, and so on. So this is called the mass matrix. This matrix may not be diagonal. So if you take these basis functions to be locally orthogonal, for example, you take scale the Legendre basis, then this is actually a diagonal matrix. But if you take it to be just the 1x, x squared, and so on, then certainly it will not be a diagonal matrix. But this is a small matrix. So as I mentioned before, for small matrices, I can use hand to invert it. So I can say this thing becomes, this is a matrix times a vector. So it's a matrix times the vector times this thing. Becomes this uj, remember, I still use my old notation. Uj denotes uj0 up to uj small k. This is a small vector in cell ij which contains all the coefficients of the polynomial. So it's a P1, this is a vector of length 2, P2 is a vector of length 3, and so on. So this is the mass matrix times this small vector with respect to t. But this matrix, first of all, it's very small. Second of all, you can even take it to be diagonal. Even if you don't want to take it to be diagonal, it's not a big issue. You can always use hand to invert this matrix and multiply it here. erase it here, right? So for practical purpose, there's nothing in front of UG sub t. So this is why you get an ordinary differential equation where this part is all computed at time level n. Let's say if you use forward Euler to compute this guy, so it would be uj plus 1. The computation would be uj of n plus 1 minus uj of n divided by delta t plus something which is at time level n equals to 0. So this is an explicit scheme, right? So you compute uj of n plus 1 just by evaluating something at time level n. These are the something you need to evaluate. So this is very easy to implement, at least for all, it's very easy to implement. It's like find a different scheme because you have your solution at un, then you do some computations using those coefficients, you get the residual, and then you update your coefficients next time explicitly. Great. So computer implementation is not a big issue. Then, of course, you say, well, the command is too inaccurate. So then later we will convert it to higher order combination of forms. So this is the implementation part. So we can say that the method is reasonably easy to implement. Now, let me, yes.
Will they hold for any delta t? These equations? Will they hold for any delta t? Will that have a stability constraint?
Oh, of course, yeah. So then I will come to that later. Okay, of course. Okay, so let me further convince you that this is very similar to a finite difference scheme. And I think this is necessary that I would want to convince you it is a finite it is sometimes can be written as a finite difference scheme. The reason is that there are people who are only comfortable with finite difference schemes. So I don't know how many of you, or some of you, might be from aerodynamics or in particular aeroacoustics. Anybody who have exposure to aeroacoustics, in aerodynamics. And if you are, you would know this guy, it's a famous guy, in Florida State University. Is a big shot in designing very accurate schemes for aerodynamics, aeroacoustics. But he was only in finite difference. So I told him this DG. Oh yeah, what is this? so then I have an idea. So I will rewrite the DG to be completely a finite difference scheme. So let me do that. I think this is a useful exercise that to convince you that the DG is just a finite difference scheme, at least for this equation. For aeroacoustics, the equations are linear. So for this equation, let's try to attempt to write DG completely as a finite difference scheme. So how do I do that? Remember, I have the freedom. The method is completely determined here. So once I write this down, the method is already determined. Once I choose my hat, method is completely determined. But different people can choose different bases to implement the method. So I always tell students, you choose your basis that you like. So the two of you choose different bases, compute. At the end of the day, you report to me. Up to round of error, you should report to me identical results. Because mathematically, it's the same algorithm. It doesn't matter which basis you take. Of course, there could be round-off errors, so the results may not match in 15 digits, but they should match up to round-off error. So since I have the freedom to choose basis, why don't I choose such basis? Let me do the following. So I have this idea, uniform mesh. Let me see, suppose it is P2. So I have three basis functions there. I pick three uniformly distributed points, including the right boundary but excluding the left boundary. So I take these three points to be my so-called match points. Fake, right? So these points are used only to define these basic functions. I pick these three guys, so each distance is delta S over 3. Then I define my phi 1 of j to be the function which is 1 here, 0 at these two certainly is 1 here and 0 here. So these three second-order polynomials, you can check their basis because they are linearly independent. So they can be used as the basis set. So then what is good in choosing this particular basis? Well, if I choose this basis, then these guys will have meanings. These coefficients, if I choose this basis, then this guy equals to the point value of the solution at these circles, at xjl. So I call these circles xjl. So this is xj1, j0, sorry, xj1 and xj2. So these 3 points are denoted by xj0, xj1, xj2. So then these coefficients, before these coefficients are just coefficients, they don't have any vivid meaning. But if I pick this kind of basis functions, then these coefficients are point values. This is done also in finite elements, right? People do this. So then these coefficients have geometric meanings. They have meanings. These are point values of the solution. And then how would my scheme become? So first of all, I have to explain what do I do with the f hat. Well, for ut plus ux equals 0, fu equals u, I will use uplink. So I will take u minus as my flux. So in other words, here I would use u minus. Here I will also use u minus. Then in the computation, I would get basically u of n plus 1 sub j equals to u of n sub j plus. Okay, so these guys are complicated, a lot of things, but I wanted to know how much it depends on what, right? Of course, it depends on uj itself, because a lot of things depends on uj itself. There's volume integration and some of the fluxes. It also depends on neighbors. But if I take this flux, it depends on neighbors in a very nice way. First of all, it depends only on the left neighbor, because the flux is u minus. So when I'm computing ij, I only need to use information on ij minus 1. I never use information of ij plus 1. So it will only involve, usually it only involves j minus 1n, but I claim it doesn't even involve that much. This is because I have chosen basis functions in a nice way. It depends only on my left neighbor polynomial evaluated at j minus half. Right? You can see here, it's u minus evaluated at j minus half. U evaluated at j minus half in this particular choice of basis is just what is my notation? Now I'm in really big trouble. 2 of n. You see? Because these coefficients have meanings now. They are the point values of the solution at the 3 circles. So here there are point values of these things at these 3 circles. And this circle here is exactly j minus half. So that is exactly the 3rd coefficient in this particular expansion, not in every expansion. Choose a different basis, then all 3 numbers will be needed. But if I choose this particular basis, I only need the last coefficient. So I only need j minus 1, just one number, the 2nd guy. Am I okay here? I don't know if you have picked up this. So then, here I can tell Tam that my scheme looks like this. My scheme is u of L of j at n plus 1 equals to, this depends on a combination of, well, let me first put this here, z plus theta t over theta x maybe times B, I used the B already, right? So let me use this way. A0, uj0, A1, uj1, A2, uj2. So I need to use all three of myself, which is here, right? Plus, let me put L here. Apologize for these indices, but these are constants. Plus just that. Plus BL of uj minus 1, 2. I only need my neighbors, 3 coefficients. I only need one of them. Third one, because the third one is exactly the point value at the interface. That's all I need to compute the flux. Right? Find a difference. You see, in order to update this point, my stencil is these 3 points plus this. So it's a 4-point stencil. Right? In order to update this point, I also have a 4-point stencil, still the same. Of course, this stencil, relatively speaking, there's only 1 to the left and 2 to the right. And here I have 2 to the left, 1 to the right. So this is not a traditional finite difference. This is sort of a group finite difference. So in each group, every point in the group is updated differently. The group consists of 3 guys. First guy is updated by a formula. Second guy is updated by a different formula. Third guy is updated by yet a different formula. But the stencil is always 4 points. So my P2 DG polynomial can be considered a finite difference scheme on a uniform mesh of a stencil of length 4. It's not optimal, right? Because if you think about it, if I have 4 points, I could get third order, but this, no, I could get, this is third order, I could get fourth order, right? The 4 points, I could get fourth order, right? Yeah. But anyway, this is good enough for 10 because it's a very different scheme. It's defined on a uniform mesh. Right? I can compute those coefficients as my student computed those coefficients given to him. So look, it's just a scheme. It's the difference between this scheme and your Euro finite difference scheme is that the Euro finite difference scheme, every point obeys the same pattern. Here, every group obeys the same pattern. The first point in the group is updated differently than the second point in the group. It's differently than the third point in the group, and so on, right? So each point in the group is updated differently. So he's happy? He's happy. So he's now collaborating with me to compare. Very happy. He's very happy. Yeah. So that's okay. So let's compare. Yeah. Because he optimizes all those coefficients. And what we have shown is that we don't optimize. We just give them the DG coefficients is comparable results. So this is already optimized in a way. Some magic playing here. Okay, so what I want to tell you is why do I say implementation first? Because you really need to code. Because otherwise you don't know what the DG is. It's an abstract thing. You prove a lot of theorems, but yeah, you want to make sure you understand what is the essential ingredients of DG. So DG is an explicit method, looks very much like a finite difference, and in this particular way, you can even write it explicitly as a finite difference. Of course, this depends on how you choose the basis. Choose a different basis that is not this way, but mathematically, of course, they are the same. Method is completely determined at this level. It has nothing to do with how you choose. Okay, so now let us explain a little bit the properties of this scheme. First of all, the scheme can be implemented and so on. You can throw a Roche-Kuta here. Then of course there is a stability issue mentioned, time step, which I'll mention later. But how about before you discretize time? How about this semi-discrete DG scheme? What can you say about it? Is this method stable? Is this method accurate? How does it work in smooth case? How does it work in the discontinuous case? All these questions. So let me attempt to address these issues a little bit. So first, there is a very good theorem about the stability. So this scheme is L2 stable. So we are trying to prove the cell entropy inequality of dg. So cell entropy inequality, you know, entropy inequality is like this, right? If you have an entropy, then the weak solution, which is what you look for, the entropy solution satisfies this additional conservation law. But this is not an equality, this is an inequality, right? This is what distinguishes the solution you want, the entropy solution from many other weak solutions. So we want to mimic this. So we take this U to be the square entropy. This is for scalar case. And I want to show that this inequality holds for the solution, for the numerical solution from the DG scheme. So how do I do that? Well, I can do the following, because this is the abstract definition of the scheme. So for this, equality holds for every V in VH. In particular, because this is Galerkin, the test function space and the solution space is the same, this is crucial. If it's a patch of Galerkin, the proof is much, much harder. So that is why people do not want to use patch of Galerkin, even though patch of Galerkin have a lot of other freedom, right? Because Galerkin is a special case of patch of Galerkin. So if you are allowed to use patch of Galerkin, certainly you have more freedom. You can throw in a lot of additional properties, but it could also mean that you will lose some flexibility, especially in this stability business, because you cannot take V equals to UH for patch of Galerkin, but you can do it for Galerkin. So let's take V to be UH, which is certainly in VH, then the equality should hold, right? The equality holds for every V, so in particular it holds for V equals to UH. So let's write down what the equality you get. You get UH sub T times UH ij plus minus, ij f of UH sub x dx plus f hat. Just let me use the shorthand notation. So the f hat denotes this thing of UH j plus half minus f hat j minus half UH j minus half plus equals to 0. So this is the equality we get by simply using the scheme and taking the test function v equals to h. So let's start from this and just the remaining thing is just algebra. So I claim that this already gives me my desired entropy inequality. So this. So why is that? Well, for example, the first term is just the ddt of ij uuh dx. Is it right? Because if you take ddt of u square over 2, you get 2 cancels with 2, u times u times ut. Okay. So you get this is exactly this. First term matches. And the remaining term, I hope, becomes a flux difference plus some positive back. So let me see this guy. This guy, I don't like it because it's an integral over the cell. I want everything to be on the boundary because I want to mimic that inequality. But it's not a big deal because I could define this function gu to be the integral of fu, the primary function of fu. So then this thing is just, this guy is just guh sub x, no? because GUH sub x is G prime of UH sub x. And G prime of U is just f of U. So this thing inside ij is just this guy. So inside ij is a perfect derivative, so you integrate, you get the boundary contribution of this guy. So basically you get this thing is G of UH at J plus half minus G of UH at J minus half. However, never write it this way because this makes no sense. You always remember for DG, whenever you write things on the boundary, it's not single valued, so you have to specify what do you mean, right? So just keep reminding yourself, never write things like this. So what should it be? Well, you are integrating inside the cell, so you get the boundary. Of course, the boundary should be from inside the cell, so it should be this way. And the right boundary should be reading from the left boundary, because you are just integrating somebody inside the cell. You never talk to anything outside your cell, so you should get boundary contribution only from inside the cell. So this becomes this. This you just copy down. UH J plus half minus f hat. Apologize. Notation is a bit. DG, I guess people got scared because of the notation. Too many indices. But the essential thing is not that difficult. Okay, so you just get this thing, right? This equality. Now, let me rewrite it in this way. Let me rewrite it as what I want. In other words, let me rewrite it as f hat J plus half sub entropy flux minus the same entropy flux J minus half plus something else at J minus half equals to 0. So let me explain to you what I'm doing, right? I pick everybody at J plus half, which is not too much, just 2 terms. And that is my f hat. So my f hat J plus half is nothing but minus G of U of H minus J plus half plus f hat J plus half UH minus J plus half. So what I'm doing is that I'm just collecting everybody at J plus half and call it something. Of course, then I have taken care of everybody at J plus half. Then I forcefully put minus J minus half here. But unfortunately, of course, my real quantity at J minus half do not match with this because I have the G with the wrong direction here. I have the G plus here. Here, f hat is okay, but this also I have the wrong direction here. So if you insist on writing it this way, then the theta has actually 4 terms. The 2 terms which were already there, and the 2 terms because you have subtracted something which doesn't exist, you have to add it back. So theta actually has 4 terms. Let me drop the index J minus half because everybody's at J minus half for theta, but everybody's J plus half, I have cleaned it with this guy. So everybody's at J minus half. There are 4 terms. The 2 terms, original 2 terms, is G of U plus. Let me also drop the H. So G of U plus and this minus f hat of U plus times U plus. Everybody's J minus half, so I don't write it. So these are the 2 terms plus f hat. You have subtracted f hat, you have to add it back. These are 2 more terms. F hat, the definition is here. So it is minus G of U minus plus f hat of U minus. Is that right? So in order for this equality to be the same as this equality, theta has to be defined this way. Then f hat is defined this way. Am I okay? I'm doing nothing. I'm just recollecting terms. Okay. Now, what do I need to show? I want to show, first of all, this f hat is consistent with that capital F. It is indeed an entropy flux. after I've shown that, I have to show theta is positive. Because if I can show theta is positive, then this part is negative, less than or equal to 0. So then this time, the part will be less than or equal to 0. That's exactly the cell entropy inequality I need. This is exactly a discretized version of this entropy inequality I have out there. So I need to show two things, right? One is this f hat is consistent with f. The other is theta is positive. So let's try to show that. Both of them are very easy. So one thing good about PG is that everything is trivial. Everything is trivial. I hope to carry this message through in the lectures. It's trivial. So because what is F, capital F? Do you know? I think you know how do you get the entropy flux, right? You go this way. You have this equality. Assume everything is smooth. You multiply it by u prime of u. It's still an equality. And then this multiply that is this. This multiply that is everything is smooth. I can use chain rule. Is this f prime of u, u of x. Then this should be capital F prime of u. Then this whole business then becomes fu sub x, right? So this is how you define this capital F. So capital F is the integral of u prime u f prime u du. Because f prime of u is this, so f of u is this. This is the entropy flux. Up to a constant doesn't matter. So I'm trying to say that this guy is consistent with that. So in other words, if u minus equals to u plus, I get that. So let me see if I'm okay. I hope I am. Otherwise, I cannot say it is trivial anymore. So let's see. So what is f hat of uu? F hat of uu would be minus g of u, right? Minus g of u plus f hat. If u minus equals to u plus, f hat is just f times u. Is this equal to this? This u prime of u is u, is small u, because u prime, capital U is a special flux, u squared over 2. So, okay. Don't worry. They don't look exactly the same, but okay. So this is u prime of u, no, small u, sorry, times dfu. Because f prime u du is dfu. And I do integration by parts, I get u fu minus fu du. Right? Integrate by parts. So this thing, I have my definition, this thing is my GU. My GU is FU integrated. So this is GU. So see, it is minus GU plus U times FU. So this flux is consistent. Is this thing positive? Well, another thing to verify is that that guy has to be positive. I hope it is. So theta is, let me group terms. It has g of u plus minus g of u minus plus or minus f hat times u plus minus u minus. Right? So 4 terms, I group them this way. And these 2 terms, I use the mean value theorem. These 2 terms becomes g prime at some c u plus minus u minus minus f hat u plus minus u minus. So I pull out u plus minus u minus. I will get g prime. G prime is f because g is the integral of f. So G prime is F. So it's F of C minus F hat times U plus minus U minus. Now the question is this quantity positive? Okay, let me rewrite it a little bit. Make your life easier, my own life easier. Let me rewrite it using numerical phrases. I write it as this: F C minus F hat U minus U plus. Let me add and subtract. So let me add F C U plus and add F C U plus. Add and subtract the same thing. Times U plus minus U plus. Okay. I can do this, right? F C is F hat C. Consistency of the numerical phrase. F hat U plus U, this is just a definition. I just didn't write it. Okay. So two situations. If U plus minus U minus is positive, that is U plus is bigger than U minus. Let's say bigger, because if it's equal, this thing is equal to 0. U plus is bigger than U minus. C is always between U plus and U minus. So this is the relationship. Now let's look at this difference. The first argument is the same. The second argument, C is less than U plus. F hat is a monotone flux. Where did it go? F hat is a monotone flux, so it's an increasing function of the first argument and a decreasing function of the second argument. Hence, it's a decreasing function of the second argument. This is smaller than U plus, so F of this is bigger than F of this. So this term is positive. Am I okay? Right? This is smaller than that, but F hat is a decreasing function of the second argument. The first guy is the same. So F hat of this is bigger than F hat of this. Same token here. C is bigger than U minus. C is bigger than U minus, and F hat is an increasing function of the first argument. Hence, F hat of C is bigger than F hat of U minus. Hence, this term is also positive. Hence, this whole product is, the whole parenthesis is positive, and this is positive, so the product is positive. Then you may say, what happens if U plus minus U minus is less than or equal to 0? Then you repeat this. So believe me, repeat this, you can show that in that situation, the product is also positive. But the product is always positive. That means theta is always a non-negative quantity. But theta plus this caboodle is 0, so if theta is positive, this caboodle is going to be negative. Yes, we have a question. Okay. So this proves that the cell entropy inequality. So we have now proved that this thing I'm cheating, right? Blackboard, I can use this. We proved this fact, which is the so-called cell entropy inequality, which directly mimics the entropy inequality upstairs. So that means the solution you computed by DT at least satisfies one entropy inequality, which is usually enough if you have a scalar conservation law with a one-dimensional scalar conservation law with a convex small f. Then one entropy inequality is already enough. Of course, if you have a non-convex, then it's not enough, but at least you have something. And also, I claim this something has also stability meaning. This is well known. Entropy condition is actually a stability criterion. So what is the stability? The stability happens to be L2 stability. So if you consider compact support boundary condition or periodic boundary condition, then if you sum over J, then you get ddt of, let's say, 0 to 1 of UH squared divided by 2. So this is this guy. You sum over every cell, you just get the whole integral from 0 to 1 of U of UH. U of UH is UH squared divided by 2. Plus, these guys just telescope, they disappear, right? So you have apparity plus half, 3 plus half minus 3 minus half, plus 3 minus half is 2 plus half, and so on. So they all disappear except the very end. But the very end, if you assume periodic boundary condition, or if you assume everything is 0, constant boundary, then they also disappear. So then, this you need periodic or compact boundary condition. So this is stability, L2 stability, or rather I should say L2 boundedness, the numerical state. So this is to say, if you don't discretize time, use your DG method, you compute a piecewise polynomial, then the L2 norm never increases with time. So at least you will never grow up in L2. This is the good old DG, right? No limit, no nothing. It's just a very, very simple method, and it has this strong property. And it doesn't matter whether your solution has a sharp or not, because this is an algebraic derivation. I did not use the PDE at all. I just used my scheme. So if your PDE solution has sharps, it's okay. So you still have this control on your L2 norm. This alone is something very remarkable because you are solving a nonlinear PDE. Right? And you get this nice result. Okay, so this is stability. Oh my goodness. So I'm way behind the schedule. I will say a few more things, then we will break for the morning. I still would like to say a few more things of hyperbolic equations because, in my view, DG method, the most successful story about DG method is hyperbolic. Even though nowadays people use DG for all kinds of equations, so you can increase the number of papers you can like, including myself. But yeah, so really for hyperbolic, it has this real advantage in my view. It's really nice, right? You have all these nice results. So let me remark that this is a semi-discrete. What happens to fully discrete? So suppose you use Roche-Coulter in pi. There are certain Roche-Coulters which is in the notes, I will not repeat, which are called TDD Roche-Coulter or SSP Roche-Coulter. These methods, these Roche-Coulter methods are convex combinations of all our forwards. So if you use those Roche-Coulter methods, you have a similar cell entropy inequality, but we can prove it only for the linear case. For up to now, we are still working very hard. Open problem, you guys can all try it. So equipped with TVD Roche-Coulter, can you prove similar? So this would be the discretized. Can you prove a similar cell entropy inequality? Now this is done by Zhang and Xu in probably in this notes. If not, then you can get it from my website for linear conservation of Fu equals to U or constant times. So this is fine. Non-linear, the story is the following. Even the linear is not easy to prove. So we proved several years, maybe 2 or 3 years, and my collaborator Chang Zhang, so he proved this. I said, yeah, this is okay. Let's beautiful. So let's see, non-linear. Oh, non-linear is trivial. Tomorrow I'll give you non-linear. So tomorrow. Yeah, no. Not that trivial. So it's still open, right? So non-linear. So this cell entropy inequality can be fully discretized space-time with Roche-Coulter. So if you use implicit time discretization, then this again is true. That's in the original paper of Jiang and Xu. But if you use explicit Roche-Coulter, it's true.
Implicit for non-linear is fine.
Excuse me?
Implicit for non-linear.
Yeah, for non-linear, for anything, because implicit is even better. So Planck-Nicolson up to backward Euler, so you have even extra term, extra good term. The bad thing about this explicit is you have an extra bad term, which you have to control. And you cannot use any regularity, so that's the trouble. You cannot, it has to be purely algebraic derivation, right? Because you cannot use any property of the PDE. I will still start with hyperbolic. We will just talk a little bit less about other types of equations because I still want to show you how you prove error estimates in the simplest setting of ut plus u equals 0. So this is for those of you who are more mathematical oriented. And then I will want to talk about some practical issues. For example, what happens if you have strong shocks? You need to use limiters. Then what do you do? Here, there's no limiter, right? No limiter, you already have this. So, by the way, this property is true also for symmetric systems, nonlinear symmetric systems. There's a paper on that. So it's a very general result. So if you have a symmetric system like a frigid system and other things, ODG method usually get this L2 control. Okay, so let's break here. We will resume at 12 o'clock.